13.1 is double integrals and rectangular regions. That's our ultimate goal at the end of 13.1 is to understand double integrals and rectangular regions. Before we jump into that, though, we have to talk about what exactly we do when we see an integral that has several variables in it. When I teach Calculus 1, I always have people who get mad at me when I ask them to write out integrals and they leave off their dy or dx. Even in Calculus 2, I take off a couple points if I ask them to write out an integral and they leave off the dy dx, and I take a point or two off. They're like, oh, well, that's so obvious you need a dy dx. It's just understood. But now that we're in Calculus 3, it's not understood because you have to indicate what variable you're integrating with respect to when there's multiple variables. Okay, so that's why in Calc 1 and Calc 2, we've got to get in the habit of putting it there because it's important. In Calc 3, it's important. So just like with partial derivatives, we just have to indicate what variable we are applying our antiderivative rules to. Now, there's not going to be any new antiderivative rules. Just the fact that we're applying it to a function of several variables is what's new. And the way that we indicate that is with the dy or dx or dz at the end of the integral. So if we were to say integrate x squared y cubed dx, the dx means we want to integrate with respect to x. It means x is the variable in that problem, and x is what we need to apply our antiderivative rules to. Any other variables we just treat like constants or coefficients. So just like we did with partial derivatives, same exact rules with partial derivatives. So what we're looking at is that piece right there to tell us how to do this problem. So the dx tells us that x is the variable here, and we just treat the y as a constant or a coefficient. So we just have to apply our antiderivative rules to that x squared. And because it's times y cubed, the y cubed is considered a coefficient, and with antiderivatives, coefficients just get carried on to the next step. So antiderivative rules say, for powers, say add a power and divide by the new power. And we're going to do it to the x, because it says dx. Mm-hmm. I like to write my I like to write it as coefficients. I don't care how you write it at all. So if you like to write the whole thing over 3, that's perfectly fine. We still need a plus c, and that's something that's going to be a little bit different for these problems. We're not evaluating this function at any limits. So it's an indefinite integral. So there's going to be some arbitrary constant. So we're going to still have a plus c. There's going to be a trick to it though, because what did we just write to the right of that c? We said something was considered to be a constant / coefficient in this problem. Look to the right of the plus c. Somebody read the sentence that starts with treat.
Treat y as a constant or coefficient.
Treat y as a constant or coefficient. In this problem, y is a constant or coefficient. So technically, that arbitrary constant could have y's in it. So our arbitrary constant could be a function of y. Your arbitrary constant could always be a function of any other variable in the problem that you were disregarding when you did your antiderivative. So if there were y's and z's and p's and l's in there, and we were only doing the antiderivative with respect to x, that arbitrary constant could have y's and z's and p's and l's in there. Because derivatives and antiderivatives are opposite operations. So if I wanted to check this, I would now take the partial with respect to x of that function, and it should give me this. And what's the partial with respect to x of c of y? It's going to be 0. It has no x's in it. It goes away. It's a purely constant, technically. With respect to x, it's a purely constant term. Any term without x's in it would be a purely constant term. So when you're doing antiderivatives, your arbitrary constant could have variables in it. It could have any variable that we were treating as constants when we did the problem, when we did the antiderivative. So our arbitrary constant is a function of any variable that was being considered a constant or coefficient. So our antiderivative is 1/3 x cubed y cubed plus c of y. Exact same function, x squared y cubed. This time we're going to integrate with respect to y. So that means we're going to apply antiderivative rules to the y, and we're going to treat the x like a constant or coefficient, depending on how and where it appears.
So 1/4 x squared y plus c x.
So our y is just a power function. It's y cubed. So we add 1, divide by the new exponent. So 1/4, y to the 4th. The x squared is multiplied, so it's a coefficient. It's just going to get carried to our answer. So 1/4 x squared y to the 4th plus an arbitrary constant. Since it's an indefinite integral, we're not evaluating it. We're going to have an arbitrary constant. We had another variable in that problem that we were just considering to be a constant or coefficient, and it's the x. So our arbitrary constant could be a function of x.
I'm sure that's CX.
C of x, or yeah. Kind of like in algebra where we say f of x. The integral of 2xy minus 5x squared z plus the sine of y dz. The middle term is going to be 5/2 x squared z squared. We're doing antiderivatives. The first term has no z's, so it's a constant. Its derivative would be 0. For the antiderivative, you throw a z on it, right? So this is 2xyz. Yep. And then the minus 5/2 x squared z squared. And who cringed when we saw the sign? On the inside a little bit, but it's really not bad because what are we just going to do to it? Throw a z on it. It's a constant term. It has no z's. Since we're integrating with respect to z, we're just going to throw a z on it. It definitely doesn't go in the angle. So as long as you don't put it in the angle and you make sure that the person reading it knows it's not in the angle, you can write it however you want. Usually to be safe, when you have trig, you would put it in front of the trig. Then you absolutely know it's not in the angle. So I'm going to write it as z sine y. If you write it behind, sometimes there might be a little confusion unless you were very specific with your parentheses. So the two pieces without z's are constants, so they just get z's attached. The piece that does have a z, we did the power rule on it. We're not evaluating, so we have to do an arbitrary constant. Yes. Yep. C of x comma y. Our arbitrary constant could have x's and y's in it. Questions so far? So the reason for that is because this is the opposite of partial derivatives. And the derivative of this with respect to z is 0. It could still have all sorts of crazy stuff with respect to x and y, and its derivative with respect to z would be 0, no matter what it had with x and y. For our definite integrals, sometimes the trickiest part, especially when you have several variables, is to make sure that you're plugging in for the correct variable. So you don't need a plus c, and you just need to make sure that you're plugging into the correct spot. And you're going to be plugging in for the variable that you're integrating for. So even though you might see x's and y's and z's, if we're integrating with respect to z, then we're going to be plugging in for z. You just leave the x's and y's alone. So with definite integrals, back in Calculus 1 with definite integrals, we always had a number answer back. Now that might not always be true here, but if you think of it with what we said earlier, with respect to x, we're considering y to be a constant or a coefficient. So in that case, if we think of y as a constant or a coefficient, then yes, it's a constant or coefficient final answer because we're considering y to be a constant or a coefficient. So there's still going to be y's in the answer, but all the x's will be gone. So for definite integrals, the first step is the same as before. We still need our antiderivative, but we don't need to put a plus c. Instead, we're going to plug in our numbers and subtract. And since we're integrating with respect to x, those numbers are getting plugged in for x. So let's start with our antiderivative. Antiderivative with respect to x. 5 halves x squared y. Minus 2/3 x cubed. And we don't need a plus c here, because it would just end up subtracting to be 0 in the long run when we did our evaluating. Now that expression has two variables, but we've only got one number to plug in. We're saying plug in 2, but it looks like there's two places it could go. It could go in for x and for y. But because we just did an antiderivative with respect to x, these numbers are going in for x. Okay? Because the original integral said dx, we are plugging those in for x. Our final answer will still have y's in it. Always plug the top number in first. So if we plug in x equals 2, two squared is 4, 4 times 5 is 20, over 2 is 10y. 2 cubed is 8, times 2 we get 16/3. 10y minus 16/3. And then if we plug in 0 for x, we get 0. So you plug your top number in first, your bottom number in second, and then subtract. So we get 10y minus 16/3. In Calculus 1, we're used to that answer being just a number, a constant. But we said we were holding y to be a constant or coefficient in this situation. So technically, we can still consider it to be a constant or coefficient. Constant answer. At least with respect to x, it is. Questions so far? Okay. All right, so just be careful with that, the d term at the end. It's really important now that we've got options. Before we had no options, so it didn't really matter. but now we have options. All right, so now the fun stuff. So double integrals we can use to either calculate area or volume. They can do a whole lot more than that, but just the most basic can be used for area or volume. In physics and engineering, you can throw a density coefficient in there and turn the volume into a mass and all sorts of other crazy stuff. But just at the most basic level is area or volume, depending on how many pieces you have in there. We can do area with single integrals. So to turn it into a double integral and still get area doesn't seem really beneficial. But to be able to go to volume is the goal. So it's kind of like just doing one baby step at a time to eventually get to somewhere better. So doing a double integral for area is not an ultimate goal. We can do it, but obviously the ultimate goal is to be able to do more than just that. Okay. So first, exactly how we do double integrals. Double integral just means we see our little integral symbol twice. There's still only one integrand. The integrand is the function we see inside the integral. It can be a function of two variables, usually. And for right now, I'm going to say dA. We integrate over an area. This is going to give a volume, and I'll tell you why. This setup has three parts to it. Each integral symbol that you see represents a dimension. And then your integrand also represents a dimension. dA means over an area. So we're looking at what's happening over a two-dimensional area on the XY plane, usually. And then we're seeing how high our surface goes above that. F of xy, some function of xy, that's another way of saying z equals f of xy. So this is a height function. So we're seeing how high a surface goes over a particular two-dimensional area in the XY plane. So we've got three dimensions here. So this calculation is going to give back a volume. Once we know what the two-dimensional area is, we can figure out whether it's going to be better to integrate with respect to x first or with respect to y first, and we wouldn't leave that as dA. We would say dx dy or dy dx, and we'll obviously get to examples of that. If it's just going to be an area, we would not put a height function in there. We would just leave it as a 1. We have to have something in there. So in this case, we're really just figuring out area. If you find the area of a two-dimensional region, and I'm going to draw this picture. The units are not going to match up, but the value will. So if we have some two-dimensional region, x by y, and I take that exact same two-dimensional region and give it a height of 1. How would I calculate the area for the two-dimensional region? It's just a rectangle. X times y. So the volume for my three-dimensional region is just a box. I just gave it a height of 1 because I've got 1 as my integrand. How do you do volume of a box? X times y times z. Our z here specifically is 1. So what's x times y times 1? X times y again. So even though a double integral can give you a volume, if you use an integrand of 1, it's really just going to spit you back the area. An integrand of 1 is just going to spit you back the area of that two-dimensional region. So the way that we calculate these things, we don't work them left to right. We work them like composite functions, where we start inside and work our way out. So I'm just going to give this an arbitrary order. So I'm just going to say dx dy. I'm just going to give it some arbitrary boundaries. Even though we don't even really need to have boundaries, we could do indefinite. So if we were asked to calculate this double integral, we work it like a composite function. We start with the innermost integration problem that we see. So we really would start by working that one. We would work the integral from a to b of f of xy dx. And that would be just like the ones that we started off with earlier. We can have a function of several variables inside of a single integral. That's perfectly fine. And we can evaluate it. We're just evaluating at the x's. Remember, we just might still have some y's in the answer, and that's perfectly fine. So this is what we do first. And we work it all out until we have a final answer. And that final answer to that integral becomes the integrand for the outer integral. Say that one more time.
It's going to look like a regular integral because you're going to got rid of the x's.
Exactly. The outer one is going to look like a normal integral. Yep. Because you're going to be down to just one variable in the outer one. Because all the x's will be gone. You'll have replaced all the x's with numbers. So the answer to this integral will become the integrand for the outer integral. So then we'll have the integral from c to d how should I write it? Some function of y dy. We'll only be left with some function of y that we got from our answer from doing the inside integral. And now it's just like a single integral with a single variable. But you do not work them left to right. You work them like composite functions. You work them inner to outer. When we work these, our inside limits of integration might have variables on them. They might not be all numbers. Unless we are working on a region that's a perfect box, where we have perfect horizontal lines and perfect vertical lines as our two-dimensional region, we might be using slanted lines or parabolas as our two-dimensional boundary in the xy plane. So we can use functions as boundaries in our two-dimensional plane. And if that's the case, then we'll have to use functions in our limits of integration. We can only use functions on the inner boundaries, on that innermost integral. So the innermost limits of integration may contain variables. They can contain variables. They can contain the variable that you have not yet integrated for. Okay? They can contain the variable of the one that's outside of them. So the innermost limits of integration may contain variables, but only if you have not integrated for that variable yet. Because if I've already integrated for that variable, I don't want to then reintroduce that variable again. If we've already integrated for that, then we've already taken care of it and gotten rid of it out of the problem. So then to have that variable in the limits, that means I'm then reintroducing it after I've already done an integration and gotten rid of it. Our outer limits have to be constants because at that point, that outer limit is the last one and we're done. There's no more to do. So those outer limits have to be constants. If we want to use these integrals to do areas and volumes, we've got to follow these rules. So the way that we decide these limits, it's exactly the same way we did area between two curves at the beginning in Calculus 2, where we did like top function, bottom function, how far left, how far right. But the way that we did it in Calculus 2 is we did top function minus bottom function inside the integrand. Instead of putting that inside the integrand, we're going to take those two pieces and just put them as the limits of our integral. So in calculus 2, the way that we did the area between two curves is we said integral a to b f of x minus g of x, where f of x was the top function, g of x was the bottom function. We're going to get this same result if I take that f of x and g of x and I put them as the limits of integration on a second integral. That way I can make room in my integrand for a height function and turn this into a volume. So now in Calc 3, really what we can do is we can say a to b f of x to g of x that way. 1 dx. Because what's the antiderivative of, and actually this is going to be, dx, dy dx, sorry, hold on. What's the antiderivative of 1 with respect to y? It's y. So if we start on the inside, the antiderivative of 1 is y. And we need to evaluate it at f of x, and we need to evaluate it at g of x, and subtract. So you plug your top one in first, your bottom one second, and you subtract. That's exactly what I just had a minute ago. But it has freed up room in my integrand to potentially introduce a new function to represent a third dimension. It has moved those functions into an integral and freed up my integrand. Okay? So we're allowed to have x's here because my dx is outside of that. I haven't done dx yet. I'm allowed to have x's on the inner because my dx is my outer. We are going to try to set up a double integral that will give us the area for this region. We've got f of x equals the square root of x. It goes through the point 0, 0, and 4, 2. And then we've got a straight line that goes through 0, 0, and 4, 2, which is g of x equals 1/2 x. We want a double integral that gives area. So our integrand is going to be 1. Now in calculus 2, we would have done top function minus bottom function to get area. So instead of doing top function minus bottom function, we're just going to do top function as top inner boundary, bottom function as bottom inner boundary. So if you look at that region, just make sure that your top function stays the top function the whole time and your bottom function stays your bottom function the whole time. Otherwise, we got to do something completely different. So what I usually tell my calculus 2 classes, just draw some little dashed lines, make sure they're always stopping and starting at the same spot. They all start at radical x and at half x. Radical x, half x, radical x, half x, radical x, half x. Radical x is always the top function, half x is always the bottom function. So whatever your top function is, that one has the larger values. So that's going to go up there. Half x is the bottom function. That one always has the smaller values. That one's going to go down there. Instead of subtracting them inside, we're freeing up our integrand to potentially put a height function later on. So this is what's happening in the vertical direction. So that's dy. That's what's happening in the vertical direction. Now we need to know what's happening in the horizontal direction, and those outer boundaries have to be constants. So we just say numbers, absolutely how far left and how far right this region goes for those outer boundaries, which is what? 0 to 4. So that would be a double integral to represent our area. Now to turn this into a volume, this could be the base of some volume where we had a surface coming up and making some three-dimensional region where this is just the shape of the base. And then we could put a height function in instead of the 1 and calculate the volume. And that would be the only adjustment we'd have to make to turn it into a volume problem. Let me actually... I'm just going to call that A because I want to do another one just like it. That's supposed to be a circle. This one's not too bad as long as we change our perspective. We don't want to go up, down on this one. We just want kind of a horizontal slice out of a circle. Most of it just looks like a rectangle, but we do have those curved ends of the circles, which are important. We want a double integral that's going to give us the area of this thing. So it's a double integral giving it area, so it's going to have an integrand of 1. What we're concerned with right now is just limits of integration. Now, if you draw your little vertical lines to make sure the top and the bottom stay the same the whole time, far off on the left and the right, the top is the circle and the bottom is y equals 1. As you move towards the middle, the top is y equals 2, the bottom is y equals 1. The top function changes. So you can split this up into 3 pieces, or you can look at it sideways. So there is a top function here. There is a top function here. And there is a top function here. Bottom function is the same throughout. So if you absolutely want to keep it vertical first, you're going to have to split it into 3 pieces. Or if you want to do it horizontal first and say dx dy, and instead see what's happening right to left, what happens when we draw horizontal lines through this region? They always start on the right side of the circle. They always end on the left side of the circle. Always start on the right side of the circle. Always end on the left side of the circle. You won't have to break it into pieces if you do this horizontally first. So if we do dx dy, that means we're looking at this graph horizontally first. That means I need to solve my circle for x. And because I'm doing y on the outside, my x limits can have y's in them. So we want to solve our circle equation for x. I want to know with respect to x, what is my lower bound and upper bound? So if we solve this for x, what are the 2 steps we're going to have to do? 2 algebra steps. Subtract your y squared and square root it. And when we do that, we technically have to put a plus or minus in front of it, which is really important because the right-hand side of the circle is the positive square root and the left-hand side of the circle is the negative square root. The right-hand side is where we have positive x values. The left-hand side is where we have negative x values. So it starts on the right-hand side, so that's where we have the positive x values, and it ends on the left-hand side, which is where we have the negative x values. All horizontal lines go from the positives to the negatives on the exact same circle. And then we can do our dy. What's this graph doing vertically? And we can only have constants, which is fine because it's got two constants for vertical bounds. What's the lowest it ever goes vertically? 1. We've got this y equals 1 bound here. And what's the highest it ever goes? 2. So this one works out much nicer if we go horizontally first instead of having to break it up into 3 pieces. And we'll actually have a better way to do circles in section 5 or section 6 when we learn about polar coordinates and cylindrical coordinates. Now we're not going to evaluate this unless Robert wants to volunteer to do our trig substitution. Because we've got a difference of squares and we don't have any u substitution partners to help us out with it. Wolfram alpha. But sometimes the hardest part is just getting it set up. And that one's a tricky one. That one's not an easy one. Need to let you have a break, but this one's kind of backwards. Wants us to sketch the region described by the double integral. It's not a difficult one, but it's a new one. We haven't done one like this yet. It's just opposite of what we were doing in the last two. So in the last two, we had the picture. We wanted to create the integral. Here, we're given the integral. We want to create the picture. So remember what order we do these in. If you look at your innermost integral, it says dy. It's telling us what's going on vertically with the graph. dy is our vertical axis. You could literally, since you see dy there, set y equal to those two functions. And that is your top function and your bottom function. Since this says y, you have y equals 2x as your top bound, and you have y equals x squared as your bottom bound. So y equals x squared is a parabola. Y equals 2x is just a straight line that goes through 110024. Oof. No, it doesn't go through 24. Oh yeah, it does go through 24. It doesn't go through 11, sorry. It goes through 1224. So there's y equals x squared, y equals 2x. That was given to us by those inner boundaries. The outer boundaries are for x. X is our horizontal axis, which means horizontally, we're only going 0 to 2. So here's x equals 0 and x equals 2. So it looks like we're dealing with that. Now the only difference when we start going to volumes is our integrand is not going to be a 1. We're going to throw some function of x and y in there. It's just going to represent how high we're going above this base. So right now this area is representing the base. And if we throw something other than 1 into our integrand, it's going to tell us how high above the base we're going. So it's going to be our third dimension. So the double integral is representing area of the base. We're going to have a break. When we come back from break, I'm going to have a couple of problems for you guys to try by yourself. Questions so far first? So you can keep walking. Questions? Okay. So I'm going to put a few problems up that I want you guys to try. Okay. And it's going to be a little bit of everything. Oops. It's cold. It's cold. So the first one is just evaluate it. Just find the value of that double integral. 1 to 3 and then 0 to pi over 2 of x sine y dy dx. And then number 2, we'll talk about what exactly this says, but it's a lot of kind of crazy math notation. So number 1 is all set up and ready to go. And we just want to evaluate it. Number 2 is the same exact type of problem, but they don't have it set up and ready to go. So you need to insert your limits. How you insert them is up to you because the limits are just constants. So it's a rectangular region. When they're constants, x is going from 0 to natural log of 2. Now, it's not a pretty number, but it's still a constant. So those are just two vertical lines. And then y is going from 1 to natural log of 3. Now, natural log of 3 is not a pretty number, but it's just two horizontal lines. Okay? So we've got two vertical lines, two horizontal lines. When it's a rectangular region, everything is interchangeable. You don't have to be careful about doing vertical lines, checking top boundary, bottom boundary, or seeing if you need to switch it to horizontal bounds and doing right boundary, left boundary. So it's just like number 1. You just have to kind of write it out yourself. So I'm going to give you guys a couple of minutes to try those. I'm going to walk around and see if anybody needs any help. Both of these are considered section 1 problems. So apparently in section 1, we were supposed to stick with constants in our bounds. And then in section 2, we could start putting variables in the bounds. So at the point where I started putting variables in the bounds, we actually were in section 2. Okay, number 2 says evaluate the double integral. So we've got a double integral and an integrand. But this time they gave the region separately. So x is going between 0 and natural log of 2, and y is going between 1 and natural log of 3. So they wrote that out separately instead of in your double integral. So it's the same exact type of problem as number 1, except you actually need to take those x bounds and y bounds and write them in there in the double integral yourself. But it's still a rectangular region. So, I mean, you don't have to check like top and bottom, left and right, and see what order you can do it in. When it's a rectangular region, you could do whatever order you want to. You could do x first or y first. It doesn't matter. It's up to you. They're interchangeable. So if we were to draw that, x goes from x equals 0 is the y-axis. So 0 to natural log of 2. So I'll say this is natural log of 2. And then y goes from 1 to natural log of 3. So this is our region right here. So it would be perfectly acceptable to do this vertically first and horizontally second, or horizontally first and vertically second. They're all constants. None of them have variables in them. So 0 to ln of 2, 1 to ln of 3. They're all constants. It's only when you have a curve as a boundary that you need to be careful with, like, who's on top, who's on bottom. Should I do top, bottom, or left, right? Does the bound change? Do I need to break it apart? But if it's a rectangular region, it doesn't matter whether you do x first or y first. It's up to you. Yes. You just need to choose one. It's not irrelevant. It's just, it's your choice.
Right.
It's your choice.
Mm-hmm. Up or down.
Right. Your choice. It'll work both ways.
And curves or whatever, you make a mistake, turn it wrong. So.
Right. Yep.
All right.
Yep. The rectangles are easy because it'll work both ways very easily. So the first one we should get 4. For the second one, don't worry about keeping it exact or doing some crazy algebra simplifying. I would keep it exact until the end. If you round it too early and then keep rounding it along the way, it will throw your final answer off a whole bunch. So just keep those ln of 2s, ln of 3s along the way until the very end and then plug it in, and you should get about 0.805. Say it again?
I was thinking about split back, so I can some interesting stuff. Split up those e's,
You can.
and then they'll start disappearing.
Yes. You could split up the e's. You could move the coefficient in front of the 2 ln of 3 up to a ln of 3 squared. And then the e and the ln will cancel out and leave you with a 9. Yeah, there's a bunch of different things you could do where you could get pieces of it to come out exact.
I'm not sure.
But all of it won't. Because at the back of it you have one of them is has a +2. So that's going to be an e squared, which is not a nice,
Number.
right, that's going to be an irrational number. So the answer is definitely irrational. So all of the pieces with the ln's and the zeros will come out exact, but there is that one spot where we have the +2, so that the answer is definitely irrational.
Where's the book say it back?
Let me see.
I want to know.
For the exact,
Yeah.
let me see what number it was.
That's kind of
13,123. Nine minus e squared over 2. So if you did all the algebra mess down to keep everything exact, so like we said, the e squared piece is the one piece that's not going to go away. Everything else will simplify down to exact and combine. 0.805 is perfectly fine with me. 0.805 is beautiful.
The only person that would learn to do all that crap is
Well, leave that. I forgot what we've been dealing with bringing the lines stuff down. Changing the red mag from. Talk about what crap those rules. You don't use it very often. Nothing's I've learned it in Calc 1.
Yeah. So those were a couple of 13.1 problems. We're going to do 13.2 problems, and we're going to be done for today. Okay? Yes. I said we're going to do 13.1, 13.2. Actually, the lecture I did was actually both of them. So at the point where I started talking about putting variables in your limits, that was actually 13.2. So I'm going to go back in the notes and put a note where 13.2 started, because I'm going to put these notes on Moodle. Okay. So we'll start off with a fairly easy one. 0 to 2. 0 to x. Ooh. Yeah. X, y, dy, dx. This is technically a section 2 problem because we've got variables in the limits. We just want to evaluate. We just want to know what the answer is. Question number 2 says, draw the region indicated by the double integral above. So same problem. Don't worry about the integrand, just the double integral. That double integral represents a region. You want to know what region it's talking about. And does the answer to number 1 represent an area or a volume?
So it would have been area times 1. Right?
Yes.
Anything that's not 1's above.
Mm-hmm. So I'm going to give you a couple minutes to work on this one. I'm going to walk around, see if anybody has any questions. What do we get when we just work out the double integral? 32. Anybody else get that? 2. Any more answers? 4. 32, 2, and 4. Okay, so maybe we should work this out. Let's work this one out. So we've got 0 to 2, 0 to x, xy, dy, dx. So the antiderivative with respect to y is going to be 1/2 xy squared. And we need to evaluate that from 0 to x. So right now I'm just working inside my square brackets. And I'm plugging in for y because I just integrated with respect to y. So I'm going to plug top in first. And that's going to give me 1/2 times x squared, which is really 1/2 x cubed. If I plug in 0, the whole thing is 0. So my new integral, or my new integrand, is 1/2 x cubed, and I need to integrate that from 0 to 2 with respect to x. So with respect to x, we're going to add a power, divide by the new power, so that's going to be 1/8 x to the 4th. Because old coefficient carries along, and the power rule says they get multiplied together. So 1/4 x to the 4th will be 1/8 x to the 4th. Okay, yep. So then you had 2x to the 4th instead of an 1/8. What's the factor between 2 and an 1/8? That times 16. Yep, so that'd be difference between a 32 and a 2. So 2 to the 4th is 16, and 1/8 of that is 2. 0 to the 4th is 0, and 1/8 of that is 0. So we got 2. So we should get 2. This region, and I saw a couple different answers for this as well. We don't care about the xy inside. I just want to know what the 0 to 2, 0 to x means. So the inner integral is with respect to y. Y is our vertical axis. So this tells me vertically we're going from y equals x on top to y equals 0 on the bottom. Okay? And then horizontally, because that's our outer one, we're going from x equals 2 to x equals 0, x equals 0 to x equals 2. So the y equals x, y equals 0, those are graphs. Those are curves. So I'm going to draw those curves. Y equals x is a slanted line. Y equals 0 is the x-axis. So y equals x and y equals 0. Y equals x is the top boundary. Y equals 0 is the bottom boundary because y equals x is on top. It's the upper bound. Y equals 0 is the lower bound in our integral. So this is the top. This is the bottom. So we're working in between those two graphs. And then horizontally, we're going from x equals 0, which is there, to x equals 2, which is there. So we're talking about this little right triangle right here. And this particular problem is giving us a volume because we have an integrand other than a 1. So that triangle is just the base. And that integrand, x times y, is telling us how high the surface is coming above that base. Okay, last one. We're out here. So we've got y equals 2x and y equals 3x minus 9. And the x-axis. This is the region that we're dealing with. Okay. We want to integrate over that region. All I've given you is y equals 2x and y equals 3x minus 9. And the x-axis. We are using the x-axis here. which is y equals 0. This one's a little trickier, but I want you to try it. Or maybe not.
See, now I feel like it's wrong.
I'll come check it. It might be good, no matter which way we end up doing this, at the very start to mark that intersection point up here. It wasn't given to us, but those two graphs are going to intersect when they're equal to each other. So we get set 2x equal to 3x minus 9. If we do, we get that the x coordinate is 9. But we should also get the y coordinate because we don't necessarily know which one we're going to use. So we might need both of them, or we might need one or the other. So if x is 9, you could take that x value of 9 and plug it into either one of those equations to figure out what the y is. So in that first one, if x is 9, y is 2 times 9, which is 18. So they intersect at the point 9, 18. So if we end up needing the x, we would go 0 to 9. If we end up needing the y, we'd go 0 to 18. So the trick with this one is if you do this vertically, the bottom boundary changes. Okay, over on the left, the top boundary is 2x, the bottom boundary is 0. But over on the right, the top boundary is 2x, the bottom boundary is 3x minus 9. The bottom boundary changes. And that's okay, but you would have to break it up into two problems, which is not always fun. It might be worthwhile to look at this thing horizontally so you don't have to break it up. So if we look at it horizontally instead, horizontally, on the right, it's always starting at 3x minus 9, and it's always ending at 2x. No matter which of those dotted lines you look at, on the right, it's always starting at 3x minus 9, and it's always ending at 2x, every single one of them. So we're going to do this thing horizontally so we don't have to break it into pieces. So horizontally, which axis is the horizontal axis in our xy plane? The x-axis is our horizontal axis. That means we're going to be doing dx first, and we need to solve those equations for x. So since it's easier for us to look at this function horizontally first, we need to think of everything kind of horizontal minded first. Everything in terms of x first. So we're going to do dx first, because that's our horizontal axis, and we're doing this horizontally first. And when we look at those two equations, it's 3x minus 9. It hits first. You always move towards your axis. So we're moving this way. It hits 3x minus 9 first, and it hits 2x second. Since we're doing x first, remember those bounds we could always write as x equals the bound. So we need those bounds written as x equals equations. So I need to solve them for x. So this is y plus 9 over 3, or 1/3 y plus 3. Doesn't matter how you write it. And this is y equals, x equals 1/2 y. So it starts on the, I'm going to say 1/3 y plus 3. That's the one that's farther from the axis. That's the one that's creating more area.
Hello, people.
Hey.
We still happy?
Yes.
Almost there.
Because we're about to
Give
leave.
us A's. We appreciate y'all. Okay. I just want to tell you that I didn't get my meeting today, but I'm gonna go for tomorrow.
Okay, okay,
You got a board meeting.
okay. And then the second integral we're going to do is the y integral, which is what's happening vertically. So vertically on this graph is the y-axis, which is 0 to 18. So that's the setup for the integral. All right? So now if we actually want to calculate it, antiderivative for 1 with respect to x is just x. And then we'll do top minus bottom. We're just plugging those in. So this just ends up 0 to 18 of 1/3 y plus 3 minus 1/2 y dy, which is negative 1/6 y. And then negative 1/12 y squared plus 3y. I don't even know what 18 squared is. Plug in 0, we're going to get 0. So we just need to know what it is at 18. So 18 squared divided by negative 12, we get negative 27. And then 18 times 3 is 54. So we get positive 27. And based on what we've said so far, is that an area or a volume? It's an area. Yeah, because we just had a 1 in our integrand. You could make an argument that it's a volume and the height happened to be 1, if you wanted to, as long as you gave a reason. But for us, we're just doing this for area because we just kind of left the integrand as a blank. And we need a 1 placeholder. There always has to be an integrand. But technically, this is just an area problem. Okay? Okay, so this one's easier to do sideways, which means we do dx first in our integration, and we want those bounds to be x equals equations, and they can have y's in them. They can have variables in them as long as you have not integrated with respect to that variable yet, so they could have y's, because we're going to do y's second in that problem. Setting up multiple integrals is the hardest part of this chapter. Setting them up from scratch is the trickiest part. Okay. So that is section 1 and 2. The only thing we're really going to do for the rest of the chapter is learn how to do some problems easier by using polar, cylindrical, and spherical coordinates. So that circle problem where we were going from negative square root of a difference of squares to positive square root of a difference of squares, that would be hell to work that out by hand. We would have to do, to work that out by hand, we would have to do trig substitution. That's what we learned in Calculus 2 for working out difference of squares when there's no u substitution counterpart in the problem available to help us. We don't want to do that if we don't have to. But anytime we're working with circles, polar and or cylindrical coordinates are going to be much nicer to work with. And they actually reduce the circle down to a constant instead of that square root of a difference of squares. So if we know we're working with circles or cylinders or anything like that, it's going to be much nicer to work in polar cylindrical coordinates. And then anytime we're working with x squared and y squared and z squared all together, we're going to work in spherical coordinates. So you may have already learned polar coordinates in trigonometry class, but we'll review it again real quick tomorrow. And then cylindrical coordinates is just polar with a z attached to it. And you've probably never done spherical coordinates, which is rho, phi, and theta. And it's very similar to latitude, longitude on the surface of the Earth. So we'll talk about that. So tomorrow we'll talk about the different coordinate systems, and then we'll look at how it can make some of the other problems easier. Okay? And we can do triple integrals as well. If we can do double integrals, we can do triple integrals. Just do it a third time. Okay. All right, we're all done.